A block with mass m equal to 5 kilograms slides down a surface inclined 36.9 degrees to the horizontal. The coefficient of kinetic friction is 0.25. A string attached to the block is wrapped around a flywheel on a fixed axis at O. The flywheel has a mass 25 kilograms and moment of inertia 0.500 kilogram meters squared, with respect to the axis of rotation. The string pulls without slipping at a perpendicular distance of 0.200 meters from the axis. A. What is the acceleration of the block down the plane? B. What is the tension in the string?
As the box slides down the ramp provides normal force on the box. There is gravity acting on the box. Tension is acting on the box from the rope. And there is kinetic friction acting on the box as it slides down the ramp at the point of contact between the box and the ramp.
So, we know that the tension in the rope provides a torque on the pulley. This means we can then sum our torques so that torque, summation of the torques, is equal to alpha I, or I alpha as some people like to write. Alpha is equal to A over R. So that way we know that A over RI equals, and the torque is the force times the distance. So the force is tension times the distance, which is R. That way we can do some simple math, so that we get A over R squared I is equal to the tension.
Okay, so we called this our y prime direction and this our x prime direction. First, we're going to sum the forces in the y prime direction. So to do that, we had to break the force of gravity into component form. So if we have the box and normal force is acting upwards, same in the diagram over there, and gravity is down, we know that that angle is theta, extending this due to vertical angles, this is theta. And if we were to drop an altitude here, that would show y right there is cosine mg, which is here, cosine theta. Cosine right there over this times mg will get you the component of gravity in the y prime direction. So to sum the forces in the y prime direction, we're going to do Fn, because that's our positive, erase this, minus mg cosine theta. And set that equal to 0 because sum of forces due to Newton's second law is mass times acceleration, and it's not accelerating in the y prime direction. Therefore, Fn equals mg cosine theta, which will come in handy later. Our next step is to sum the forces in the x prime direction. So we know that mg sine theta is acting in the positive x prime direction, while tension and force of kinetic friction, are acting in the negative x prime direction. So summing forces, we get mg sine theta minus tension minus force of kinetic friction. And we're going to set that equal to MA. Our next step is to start simplifying that equation. So we had previously solved tension to be IA over R squared. So we're going to plug in there. So A times M equals, starting with force of kinetic friction, we know that that simplifies to mu k Fn, and we had solved for Fn in the previous video. So force of kinetic friction simplifies to mu k times Fn, or mg cosine theta. So mg cosine theta times mu k. So that takes care of the kinetic friction. Tension we had solved previously to be IA over R squared. And we're going to keep the mg sine theta as it is. So mg sine theta minus IA over R squared minus mu k mg cosine theta equals MA. To further simplify that, we're going to get tension, or our newly plugged in IA over R squared, to the other side, and we're going to factor out what we're left as best as we can to get it simplified so we can eventually solve it. So, MA plus IA over R squared is going to be our left side. Sorry, the M's a little messy. Got to work on my penmanship. Set that equal to, we're going to keep an mg out because each term has it. And mg, what we're left with is sine theta minus mu k cosine theta. Alright, so just to recap, we're at mg sine theta minus mu k cosine theta equals ma plus ia over r squared. Since we're trying to solve for the acceleration, we're going to factor out an a right there. Oops, we already factored out that a, so I need to write it again. So a times m plus I over r squared. And we're going to keep this side as it is, because I don't know about you. I think it's as simplified as we can get it for now. And we also know all these quantities, so we're going to be able to plug in numbers for them to get a numerical value of acceleration. So m g mg sine theta minus mu k cosine theta. Now, sorry, forgot the equal sign. Now all we need to do is divide, and then we're going to have a on one side, and we'll be able to plug in numbers to get our answers. So, a equals, come over here, mg times the quantity sine theta minus mu k cosine theta all over m plus I over r squared. Tilt that video just so you can see it. So what we're left with our simplified, if you want to call it simplified, solution for A in terms of the variables is mg sine theta minus uk cosine theta all over m plus I over r squared.
So just to rewrite the equation so we have some more room, we put it up here. And so we know what m is, we know what g is, we know what sine, well, we know what theta is and theta is. It was given to us what uk was, we know the mass, we know what I was because it was given in the equation, and we know what r is. So by plugging in 5 times 9.8 times the quantity of sine of 36.9 minus 0.25 cosine 36.9, all divided by the quantity of 5 plus the quantity of 0.5 all over 0.2 squared, we eventually get an answer of 1.1214, which rounded to 2 sig figs is only 1.12 meters per second squared for the acceleration.
In our previous slide, we showed you why the tension equals I times A over r squared. Plugging in our value of acceleration that we previously solved, which was 1.1214 meters per second squared, times I of 0.5 kilogram meters squared, divided by the radius of 0.2 meters squared, gets you a value of 14.0 newtons to 3 significant figures for tension.